Alright, welcome back. I'm pretty excited about this episode this time because I'm going to show you a method known as the Whitney Stress Block, which is very, very powerful and very, very easy for computing the ultimate strength of a flexural member, whether it's singly reinforced or doubly reinforced. So if you recall from last time when we were talking about moment curvature relationships and kind of ductility, I showed you guys a plot and we identified 3 critical points on that plot. Okay, and in the last video we talked about figuring out what the cracking moment was and what the moment that caused the first yield in the steel, and then we kind of studied some of the parameters that were associated with it. The third point was the ultimate strength, and we started to kind of explore that a little bit, but we didn't go very far into it because the method was, while it was popular at one point and was decent for approximating the stresses and strains, it just wasn't very user-friendly, so to say. So I kind of want to rehash a little bit of what we did in that video and then set ourselves up for moving in to Whitney. So if you remember, we had a rectangular cross-section, we had a stress and strain diagram. Here's my stresses, here are my strains. Strain, again, is always linear, or at least that's the assumption based on the idea that plane sections remain plane, and so the strains are linearly proportional all along the height of the beam cross-section. Okay, recall that the location of strain equal to 0, this is my neutral axis. Okay, and that we identified the distance down as being this variable c. Okay, so this is my strain in the concrete. Normally this we take as 0.003. Okay, and then we have our stress, our corresponding stress or strain in the steel off of that. So if I know c and I know this, I can find the strain in the steel, and that becomes a very, very important idea for us. But if you remember, what we said is that the strain in the concrete didn't follow Hooke's law at this point, right? Because the maximum strain or the maximum stress in concrete occurs at a strain somewhere around 0.002. But we define the ultimate strain as being 0.003, something a little bit higher. So there isn't this linear relationship for Hooke's law like what we had here anymore. Okay, so we get kind of this strange distribution that's kind of parabolic but kind of not. Okay, and if I knew where I could find, by integrating this, I could find my C resultant, and then I could also locate where the location of that centroid was, but it's just not very friendly and not very easy, and it's very cumbersome to do it this way. Okay, and so we presented, some tables with some alpha and beta formulas, and I'm just going to show you the formula just to recap. I'm not going to go all the way through this again, but if you remember, we had a formula like something kind of like this, where rho is the reinforcement ratio, Fy is the yield stress, B and D are the dimensions of the beam, and then these alpha and beta were characteristics based off of the concrete strength, okay? And this was kind of an approximation to the distribution of stresses over that cross-section, okay? So, again, completely valid, works. It was a pretty good approximation, but it's just not real friendly and not real easy to calculate. So we want to come up with a better way. And that's where Whitney comes in, all right? So kind of the same idea that we have here. We're going to consider the ultimate strength. We're going to look at the Whitney stress block is what it's called for. All right, and so what happens is just like we talked about, here's my rectangular section, and here's my strain diagram, and here's the corresponding stresses and strains. So nothing has changed on his setup, okay? And so what we said is that at ultimate strength, the stress distribution is no longer linear, right? And that we can no longer be related to strain through Hooke's law, okay? It's just not valid. So, and the difficulty that we had that we just said is that, well, okay, I can find this by integrating the area, but where the heck is it located? That's the challenge, all right? So what happened in the 1930s, Charles Whitney was an American civil engineer and proposed the use of a rectangular compressive stress distribution with an average stress. And so this is a little bit of a trick. Instead of taking the variation in stresses that we saw here, he's going to approximate this area with an equivalent uniform stress distribution. Okay, we're going to change this dimension C to something else, and then if it's uniform, I will always know where the resultant is. It's always at the middle of that block, and so that becomes a much simpler approach to being able to do it. All right, so what he proposed in this was using a rectangular compressive stress distribution with an average stress where the stress was equal to 0.85 F prime C. Okay, and that had a depth or a rectangular region of this letter A that he used, and he related A back to that C dimension. This is the same C that we had on the strain diagram, right? That's the distance from the top fiber down to the neutral axis, and then there's this multiplier, this kind of beta 1 factor, if you will, okay? And this is the trick and the approximation, and it works very, very well for what he had proposed, okay? So what happens is when you look at the stress and strain diagram for this block, again, here's my rectangular section. This is what we were proposing and what we kind of come to the conclusion of. He took this and turned it into this. Okay, so instead of being C down, now the depth of the block, the neutral axis is still considered down here, but the depth of the Whitney block is now considered this value of A, and it's measured from the top fiber down to the bottom of the block. Now I say top fiber, that's assuming a positive moment, right, where the compression is in the top, okay? And then the magnitude of this stress block, and again, we didn't know it over here because it corresponded to the corresponding strain value. He said, well, we're just going to take 85% of F prime C. Right, and so when I do that, the rest of the diagram looks exactly the same. Here's my C res, here's my T res. Okay, this becomes the area of this block. Well, that's really easy now. It's 0.85 F prime C times B, the width of the beam, times A. That's it. It's just a simple rectangular prism. Okay, but the part that really is kind of the clincher for this methodology is now you know the location of this as simply being A over 2. All right, the block depth was A. This guy, if he's the resultant of this region, has to be A over 2 down from the top. That's it. Okay, so then the moment arm between T res and C res is just simply D minus A over 2. Super, super easy, piece of cake. All right, so here are the equations, just like we've done in the last couple of videos. We calculated C res, 0.85 F prime C, so that's my sigma. Okay, we have B as the width of the beam. That was this dimension. If that's my cross section, because this stress block acts uniformly across the cross section, and then multiplied by A. That's it. Okay, T res, again, we're hoping to have ASFY. It may actually be ASFS. Okay, but we'll solve for FS, but for yielding and for a ductile situation, we want FS to be equal to FY. All right, so then to find A, which becomes kind of the clincher, because if I can find A in this picture, if I can find this guy, then I know that A is related to C, and C gets me the strain diagram. We're back in business. Okay, and we can kind of work our way out. So all we're going to do to solve for A is just sum of forces in the X off of this picture. And just like we've done a couple of times already in this series, is we're going to say then that C res has to be equal to T res. Or if we write it in the full version, I sum forces to the left on that force diagram. Sum of forces X equals 0. And so I get ASFY minus 0.85 F prime C BA. Again, sometimes you'll see this written as ASFS, but if we want FS equal to FY, this is the equation that comes out of that. And now this guy is linear in A. So I can solve for A as being equal to ASFY all over 0.85 F prime CB. Okay, that's pretty cool. Okay, now if we kind of look at this, there's a slightly different modification to this. If you recall that rho we defined as AS over BD. Well, if I multiply by D over D, I can get rid of AS and I can get rid of the B, and all I have to do is add a D, and then I can get my rho back in there if you prefer to work with reinforcement ratios. And this was kind of one of the ways that we used to do stuff back in the day, all right? But not necessarily necessary anymore. This one's simple enough. I can just plug and go. So, all right, so then the nominal moment capacity then, all we do, just like we did before, if you recall, is I'm going to sum moments about, if this is where this guy is acting, I'm going to sum moments about that point. Okay, and when I do that, the C res goes away. I have my ASFY for T res, and I'm going to multiply it by D minus A over 2. And so that moment equation that was really ugly and really hairy with all of those alphas and betas running around in it now becomes simply ASFY times D minus A over 2. That's the nominal moment at ultimate using the Whitney stress block. Super, super, super easy. Okay, now, one of the things that we'll do a lot of times, especially in design, is we'll modify this formula ever so slightly, right? And say, so let's do ASFY times D minus 1/2 of ASFY all over 0.85 F prime C times B. And when I do that, if you look, if I know everything except for the area of steel for a given nominal moment on here, all I have to do is plug in AS, my area, and I will kick out the moment. And that's it. I can say, oh, what's my moment capacity of 3 number 9s? Plug in 3 times the area of a number 9. what's my moment capacity with 6 number 7 bars? Plug in the area of 6 number 7 bars, and it just works itself out magically off of the Whitney block. It's super, super easy. Okay, now you'll notice that it is quadratic in AS. So if I want to work it backwards and say I know the moment and I want to know how much steel I need, I can do a quadratic expansion on this thing and use the quadratic equation to solve for AS that's required for that particular moment. So it's just so elegant and so simple to be able to work with it. Okay? All right, so here's how we're going to, so the challenge in this whole process using Whitney is to find that little A guy. Okay? So it's pretty easy. Okay, we're going to relate the Whitney stress block back to our strain diagram. Again, we said that there had to be a mapping that went from A to C. Okay, because that was kind of the magic that made it all happen. Because A doesn't have any physical meaning anymore. It's just kind of this arbitrary value that Whitney chose to use. Okay, everything else is exactly the same. So what happens is once you solve for A, because again, we're building this off of, our force is 0.85 F prime C B times A becomes that value is the force for our C res. That I'm finding my A off of the forces, but we haven't checked the strains. And we made an assumption here about epsilon S that we had assumed, again, realistically, this is AS FS, but we assume that epsilon S equals epsilon Y, which will imply that the stress in the steel is equal to the yield stress. And that's our assumption that we're making. So when we solve for A, we go back, we set up our strain in our concrete as 0.003. Okay, I know the relationship that Whitney used to get A to C. Okay, and then all I have to do is I have to check this epsilon S to make sure that we have a case where epsilon S, and that should be a greater than or equal to epsilon Y. Okay, that if the strain in steel is greater than yield, we're going to limit our stress to the yield stress. Okay, now again, this may or may not be greater than epsilon Y. You don't know until you check. You've got to check the value. Okay, and so that's one of the assumptions. This is the biggie. You've got to verify that. Now, if we go through and we look, okay, he used A equal to beta 1 times C. Well, what is this calibration factor? Okay, and all it is it's a variable, just like those alphas and betas in the equation that I showed you from last video. He called beta 1 as simply being this equation, 0.85 minus 0.05 times F prime C minus 4,000 all over 1,000. So for F prime C of 4,000, beta 1 is 0.85. So there's another 0.85 running around in here. So it can get a little bit confusing sometimes with that regard. But it's basically for every 1,000 psi over 4,000, we decrease beta 1 by 0.05. And this will match or will approximate those table data that I showed you in the last video. If you're still having some questions about it, go back and just kind of watch back through it, and you can kind of see where some of these values are coming from. The idea is very, very similar. Okay, so then all we have to do to find epsilon S is we come back to our strain diagram and we do proportion. So I had A, this guy, which got me C, so I now know the proportion for the strain diagram, and I'm going to take 0.003 over C, and I'm going to set that equal to then the epsilon S that I have all over this dimension, which is now D minus C. Okay, and that's exactly what I do to find it. So again, A, which gets me C. I already know D. I can find the stress in this, or the strain in the steel accordingly. So then, if epsilon S is greater than epsilon Y, we know the steel has yielded. Our methodology was correct. If it turns out that this guy is less than epsilon Y, then what has to happen is that where we had assumed Fy here, I plug back in Fs, the actual stress that I get, and then I have to resolve it. Because if this guy doesn't get to Fy, my A gets smaller. Okay, and so it's all about figuring out what the A is. And sometimes there's a couple of iterations that have to take place on this. Hopefully, if you're designing this properly, most of the time it is Fy. And that's always where I start my assumptions looking at this method. But you've got to check it to verify, because it is a big assumption. All right, like I say, we assumed that. So that's what we're after and what we're looking to work with. Okay, so that gets us to our Mn equation. Okay, so if Mn is equal to As Fy times D minus A over 2 in this, okay, that gets us our nominal moment, but what we haven't included are any additional safety factors. So what we're going to do is we're going to always factor our loads, and we want mu, the factored load, to be less than or equal to some reduced value of the nominal moment that we're calculating. All right, so this is my factored loads. All right, and then this guy here is my reduced capacity. So it's just like LRFD that we did in steel. It's the same basic equation. So the question becomes, well, how much do we reduce it by? Okay, and this is the one thing where it gets a little tricky. For years and years, phi was 0.9, and then you just kind of worked off of a different methodology. But starting in the last couple of editions of the ACI code, they say that they're going to tie phi, the value of phi, to the strain in the steel, that epsilon S value. Okay, and if you're not yielding, phi is one value. If you're beyond a certain limit where it's ductile, it's another value, and you kind of iterate through it. So this whole thing comes out of table 21.2.2 in the ACI 318 2019 edition code. Okay, and in the table I pulled out for you just so you can kind of see it. It's pretty easy to use. Okay, so if we have that my epsilon S on this is greater than 0.005, okay, this is called a tension controlled specimen, okay, and it has a phi value of 0.9. Okay, if we go where our epsilon S is less than epsilon Y, meaning this hasn't yielded, then the nominal capacity is controlled by the crushing strength of the concrete. And so this is a compression control situation, and that's not, not necessarily a safe situation, because again, we never want concrete to fail by crushing because you have no ductility. Once it crushes, it's game over on that. So if we look, and when I was doing the last one, I pointed at the wrong column, but you notice 0.9 and 0.9, it's the same for both of these. What this is for, for any sort of spiral reinforcing, for combined moment or axial force or any other case. So most of the time you're over on this one, working on this, okay? So for the tension control case, it's 0.9, and for the epsilon S less than epsilon Y, you're at 0.65. Okay, so now what happens if you're in between these two values? Okay, because again, we're assuming that epsilon Y is equal to 0.00207 inches per inch when my Fy is equal to 60 KSI. That's kind of that magic number that I've highlighted a couple of videos ago that we keep coming back to him for 60 KSI. All right, so if you look, we're going greater than 0.005, okay, or less than 0.00207, it's well defined. Otherwise, you do a linear interpolation between the two of them. Okay, and so that graph looks something kind of like this. They give you a little bit of extra capacity for spiral because that helps protect against crushing a little bit better than non-spirals or this. And for what we do with beams most of the time, seldom do you use a spiral on a beam. Where this kicks in is if you have a column with a moment in it, typically. Okay, so we're usually this solid line here, and so this is what we call the transition zone, where I'm going from my my 0.65 all the way up to my 0.9 value, okay, for the compression controlled and the tension controlled regions. And so we're kind of looking at it. Okay, now what we want to be able to do and to look at this is, if you'll notice, and it's kind of hard to see up here, that the variable that's there says epsilon t, okay? We're used to seeing epsilon s, which was taken at the centroid of the section, and that's where d was measured to. So what you got to be careful of, and there's this diagram that's kind of on that same page that you got to kind of watch out for. Here I have a section with two bars, all right? Going to the middle of the bars got me, if I calculated the strain, which would be up at some point here, would get me epsilon s. That would be epsilon s. Epsilon t is the largest strain in the bar, in any of the bars on that side. So in this case, because the strains get bigger as I go down, we're going to go all the way down, and we're going to take the line of this epsilon t, okay, the line at the bottommost bar as my epsilon t value, and that's what you plug in to this table to determine phi. Now, a lot of times I'll cheat a little bit on this, and typically what I'll do is, if I calculate my epsilon s, which is really easy to get, the one that's at the centroid, because I have all my relationships from before on that, I'll use that as my check. Okay, so because if epsilon s is greater than 0.005, which is what I want, then clearly epsilon t is also greater than 0.005. Okay, it's only when I start getting kind of close, or start having some problems where I don't fall into this bottom range because of what I chose for my strain, will I come back and set up and sharpen my pencil a little bit more to be a little bit more accurate. But generally, there's not a lot of difference between epsilon s and epsilon t. So ACI says use epsilon t, but most of the time, just because for simplicity and speed, I'll throw in epsilon s as a little bit conservative on that. So got to be kind of mindful of this one little note here. It says reinforcement is closest to the tension face. That's where epsilon T is depicted. All right. Okay. So that pretty much sums up our Whitney stress block for us. Okay. Now, like I say, to kind of walk through the methodology, I would have work something like this. I've got a cross section that is B wide, H high, D is my depth to my single row or my centroid of my reinforcement that I'm calling AS. Okay, and what we're saying is that this is an SRR rectangle with B equal to 6 and H equal to 12 inches. I have concrete cover of 2.5 inches. So remember, that's that dimension. That's the concrete cover. Okay, I'm saying that the area of steel is 3 number 4 bars equally spaced in one layer. So that's the location of all of that AS. F prime C is 4,000, Fy is 60,000. And then I proceed to walk you through the procedure to be able to do it. Now, again, if you're taking this in one of my classes, I'll have you guys work through this in class or on your own. But, for the rest of you, you can kind of work through this process. But this is kind of the step-by-step procedure to get you through all this. Now, for any flexural problem, I always draw these two diagrams. I have a rectangular beam. I'm going to draw the strain diagram first. I'm going to draw the Whitney block second. Okay, and so you know that this is kind of a linear function with your variable C and 0.003 and all that. Your Whitney stress block in is that 0.85 F prime C for the stress and an A depth and ASFY happening here. And then it's just a matter of figuring out what your dimensions are for this particular beam. And that's what this is going to walk you through, is the calculations to be able to do that. Okay, once I do that, then we're going to figure out what are my values for the location of the neutral axis. Okay, now epsilon CU, that's just the strain in the concrete. This is almost always 0.003 when we're looking to find the ultimate moment. Okay, beta 1 is Whitney's correction factor. And then once you have little a and solve for it, I can find C. And then with C, I can get epsilon S. And then epsilon S, I can get phi down on the last part, and then with that I can get my phi mn. That's it. It's very, very simple, very, very straightforward. In fact, for years I used to just program the mn equation into my calculator, and like I say, if you rewrite it the way that I showed you with the mn equals as fy d minus 1/2 as fy over 0.85 f prime cb equation, okay, I can solve for AS straight out, or in this case, we're looking for the moment. I can just plug in values and get M in, and I don't have to do any of the A to C conversions. But you still have to check that, especially when it comes to this guy, we've got to check that epsilon T is, is that greater than, 0.005, or is epsilon S actually less than epsilon Y? Okay, because if I have that, we violate our assumption on a derivation, and we have to go back and kind of fix some things. But you've got to always make that check, and so that's kind of what we're looking to do there. So anyway, that's the Whitney stress block. It's a really powerful concept. It's super easy to use. Okay, and like I say, it's a game changer. It's so easy and so simple to be able to use that approximation, and it's, like I say, it's pretty accurate for what it is that we're trying to do, and simple, singularly reinforced. Easy for me to say, right? Singly reinforced rectangular sections. And it also works for doubly reinforced, and you'll be using a model similar to that for anything that has flexure in it on those kind of things. Now, the one limitation on the method that we have that I didn't mention before is that we can only have moment about one axis, right? And in this case, we were assuming that this was a moment that was taken about an X horizontal axis. And again, this is the double-headed arrow notation, so my moment's kind of doing that direction, flexing this thing. All right. If I get a second moment that does this, all bets are off, okay, in conjunction with this. Now, if I have just that one, then it's easy. It's the same problem. It's just now my A is coming this direction, okay? But if I have both, now we've got a biaxial bending case, and Whitney, we've got to kind of be a little bit more careful in our approach. But for just singly reinforced sections with a single direction moment, we're gold. We're good to go. All right, I'm back. As I was setting up to close down from that, I realized that there was one little piece that I failed to mention with regard to the Whitney block on this, and so we'll kind of walk you through this real quick. Okay, remember what we were doing before was all about rectangular sections, okay, and we made the assumption before that B was a constant width along the entire section. But what happens if I have a beam that looks something like this? Maybe this is an inverted T or some sort of cutback for another beam to be able to sit on it, or something like this. Okay, what happens now is I now have different B values associated with each part. So if I call that B1, and then maybe this guy is B2, and you can have multiples of these. In fact, this could be the start of the formation for the opening. Okay, the way that you handle this is you have to consider two cases, because what I don't know with Whitney on this, again, my strain diagram looks exactly the same as it was. Okay, C is this dimension, okay, and then my A was some function of C, right, based off of that beta 1 value. But what we don't know is, in this particular case, you have to make an assumption about the strain diagram that the neutral axis of this guy, falls at some point above where this change in width occurs. Okay, more specifically, even really C isn't really the issue. I'm more worried about A, right? So say this guy is 4 inches, and you turn around and solve using the approach that we did before that A was actually 3 inches. Okay, well, no problem, because that looks exactly like what we did, and everything below this point gets neglected because that's considered to be tension in concrete. Okay, we don't have a problem. But what happens if I go down to a section, and now all of a sudden, if that was 4 inches, now we say A was 6 inches, because I put so much steel in it that it pulled that A way, way, way down on here. Or maybe, it's some portion of the slab. We have an unequal distance. Now what happens is my formula has to change a little bit. Okay, and the reason that it changes is, if you remember when we calculated these resultants, my stress block looks exactly the same. I'm still using 0.85 F prime C. My A is still my height, but what happens is from this point to this point, my B is different than from the here to here. Okay, so what we have to do is we have to modify our formulas just a little bit. Okay, so a lot of times what we do is we call this as an H1. It could be a slab thickness or whatever the case may be, but the approach is exactly the same, but we have to add one extra term. So the first one we do is we find the resultant of the piece of the narrower width. Okay, and that's going to be 0.85 F prime C B1, okay, which was my width of my narrower section, multiplied by H1, because A is greater than H, on this, or greater than H1. And you can see that I have that written up here as well. Okay, C res 2 then is everything else associated with that stress block. So it's the portion of the stress that falls on that little region there. And so we do 0.85 F prime C. Now the width is B2, okay, and then the height of this block, if it's H1 from here to here, then that block there is A minus H1, and that's the correction. Okay, once we have that, then all I have to do is go in. My T-res is still ASFY. We still have to check the strains. No major problems, okay? And then just like before, if you remember to find A, you always sum forces in the x direction, but now the equation's a little bit different. All right, so now it's the sum of forces x equals 0. I have my tension, T-res, minus C-res 1, minus C-res 2 equal to 0. You have to solve this guy to peel off your A. So there's kind of this extra little chunk that gets subtracted off of the capacity because of what's happening up in that thinner portion at the top. Now again, I assume B1 less than B2. This works exactly the same way for B2 greater than B1. Okay, so you're always kind of trying to figure out what's the depth of this block, and this becomes the correction. So once you do that, it's just a bunch of algebra to get there. So all I'm going to do is I'm going to kind of solve for my A, do a little bit of algebra rearrangement, and we should be good to go. All right. So you can solve for A on this, and then we're back to solving for then the moment capacity for that second case. Okay, now what I do on this one is I'm going to sum moments about the top of the beam on there. So if we look at this, I'm going to sum moments here. Okay, and the reason I do that is a lot of times when I start doing these inverted T-beams or box girders with openings in them, when I locate these, often I know the distance from here to here, and from here to here, and from here to here. All right, so just for convenience, I'll sum moments there. It's the same equation. Okay, the moment equation still works, but so what happens is I'm going to take C res times H1 over 2. I'm going to take C res 2 times its distance to its centroid, and then I'm going to take T-res times its distance from the top to the centroid, all right? And when you do that, the equation looks something kind of like this. ASFY times D, because that's measured from the top, minus C-res 1 times H1 over 2, because that's half of the slab thickness, okay? And then the C-res 2 gets the one that's a little bit weird. It's H1, the thickness of the slab, plus half of that extra portion that was left over. Okay, so there's this little bitty correction factor that has to go in on that H1 to get us there, all right? So, but just like what we did with the simple singly reinforced sections, you know, now when we get into these shapes where things are a little bit more variable, all you're doing is you have to find the position of A in the cross section. Okay, figure out, are you case 1 or case 2? You know, once you calculate A, then you know which case you are. Okay, and then, you know, typically what I'll do is I'll assume case 1, and if that doesn't work, then I assume case 2, and then I just kind of progress my way down through it. Okay, and the approach is exactly the same. So now the type of beam that might show up, there's a couple of them that I can show you. You know, maybe I have this opening that occurs at some sort of trough beam. I mean, maybe it's an opening for conduit or something. And so what happens is that this is my B2 value. The width of this thing is 8 inches, but my B1 then is the width of this guy plus the width of this, or 4 inches. Okay, and so that's why when I walk you through the process, it's exactly the same. Here's the first case. We're going to assume that it's, you know, the A is occurring up in this region, and then the second case, the A is going to be assumed down in this region, and then everything else is the same. And so all I'm going to ask on a typical walkthrough is which of these cases is correct, because that dictates my formula. Okay, and then once we do that, then we basically solve for what is my A, and then we're off to the races to find everything else. Everything else is exactly the same as what you did before. You know, you can locate the neutral axis, we can compute the nominal moment capacity, okay, and then I can compute the design moment by finding my phi value, by doing my strains. Again, the strain diagram doesn't change, but everything else does. Okay, and with that, we should be good to go. Anyway, thought I needed to add that in there. I apologize for the strange break in what's happening there. As always, toss us some comments, leave us toss us a like on the video, and please be sure to subscribe to the channel. We'll keep these videos coming. Anyway, have a great evening, and sorry for the late minute add-on. Anyway, it's a very, very important method, but it's so useful. Anyway, have a great evening. I'll talk to you all later. Thanks. Bye.